So thanks for the organizing committee for putting this workshop together. I'm Guilherme Castelão, just Gui from Scripps Institute of Oceanography, and my co-author is Luis Ibe. I recommend you to search for him on GitHub. He has several very interesting, cool crates himself. This will be a fast-paced presentation, so I hope I can instigate your curiosity to check it out GSW on the GitHub and this talk itself. So I used to work in the instrument development group, a lab in Scripps specialized on autonomous platforms. And here on the left, we have a Solo 2 from Argo, which is probably the main revolution on modern oceanography. And these platforms, they dive. Some models can go up to 6,000 meters and come back to the surface. And this process measure different properties. And once reach the surface, contact us through satellite and transmit the data. We currently have something around 4,000 of those spread in the oceans, and that's the way how we know what's happening out there. And here's a different model, that derivation that has a wing, and for that reason call it gliders. And to a certain extent, they can kind of decide where to go. So one of the main project that I did on with Rust was exactly on the satellite communication of these platforms. On the system and the data protocol itself. And after that successful project comes the question, there's so much autonomous decisions going on these platforms, and can we do more? Can we do a wiser processing of the data on board? And what would be the requirements to build up this infrastructure? Well, the first requirement is for the platform to understand its environment, what's going on, and make sense of the raw measurements straight from the sensors. And we can do that with Gibbs Sea Water, and is basically a relation of several variables in the ocean. And we can do things like, with a measure from pressure, temperature, and conductivity, we can estimate what is the local density. Gibbs Sea Water is implemented already in several libraries, such as MATLAB, which is the one closest to the scientific team. So we take these as our scientific reference. But several of the most common languages, they are actually like Python. They are based on the C implementation. So for us, the basic requirement is be able to go embedded, but the list goes long. One important one is robustness. I didn't mention, but like Argo platforms, they can last up to 8 years without being recovered in the ocean. So without firmware change and anything, so robustness is a priority. Also be able to plug with the system that already exists without the risk of rewriting everything. I will just touch on some parts of this process developing this library. One of them is we rely on tests to guarantee our results, right, and implemented in several layers. One of them is straight on the documentation to help new users how to adopt. We have unit tests straight together with the functions, mostly working on edge cases and cases that we find on publications, so we know that we should satisfy those values, and the validation. So the MATLAB library provides a data set with a group of test cases, which we use that validator library, but this is a MATLAB binary. So to test that, we developed an auxiliary crate that serialize that using postcard and create small chunks that can be loaded straight on the stack in such a way that we can test our library straight on microcontrollers. We use FFI to expose our functions to C-compatible libraries. And for instance, Python is based on the C implementation. And what we do is we plug instead our Rust implementation, and then we run the Python tests to validate. This is integrated in our CI. And we not only validate the linking, but also we double check our results. And we do run benchmarks, not so concerned here about the details, like the numbers. It's just like a ballpark, just to give an idea if you're not doing anything really bad. And we found speeds like we do as fast as some functions as fast as 4 times, others 4 times faster, others 4 times slower than C. Again, this is not really a rigorous benchmark. It's just like to give an idea for how we're going in general. Going back to our motivation, we can achieve the embedded without not using the standard library, and by that we can support firmwares for run in firmwares for microcontrollers, but just that would limit too much the usability of the library. So we take advantage of features to allow the users to give some flavor on what they're looking for. For instance, you can choose to add the C API, but also that was an interesting part, like we can use that to make strategy decisions. For instance, by definition, we do not expect salinity to be negative, but do small errors on calibrations or rounding. Sometimes you can find tiny small negative values. And the strategy on MATLAB was to just transform everything that's negative to 0. While on C, sometimes they use a sentinel value. And we had a different opinion. And for us, the default is to raise a custom error specific for negative salinity. And we think that we can provide a better information for whatever application is built on the top. But if the user still wants to reproduce what was built on MATLAB before, you can choose compat and replicate the same behavior. One thing that I appreciate very much, especially in scientific libraries, be able to write code for humans without compromise on performance. It makes a huge difference to compare with the literature and validate, find bugs and identify what's going on. One thing that I noticed in several crates, scientific crates, is the lack of DOIs and citation. So if you're interested in that, I think it's very important not only to track scientific impact, but for reproducibility. And if you're interested, I recommend to check these 2 links. I have some suggestions how you can implement that for yourself. Some other applications that we developed in Rust, and I stop here. Thank you.
Okay, thank you very much for the self-guide. That was it's always very nice to see a very different application. You know, there's a wide breadth of things being developed in Rust. I really didn't know this. So yeah, I don't see any questions in chat right now. Yeah, I think as usual, I think that the questions might trickle in as people digest a bit what they just saw. So if you have questions for Guy, oh wait, here's one question actually. There's a question: which processor or board the ESP RISC seems to have the most development effort? Do the HAL hardware abstraction layers make this a moot point? Asks John.
So this was my wish list to develop the firmware itself on Rust. So the whole firmware itself is not there yet, and this was developed as a basic ground to start to create the infrastructure around to allow moving to that. So it's not quite there yet. Yes.
Yes, I believe there was a link also. I think maybe Matthew posted a link to the repository a bit further up in the chat. So if this is the same repository, the GSW-rs, is this correct?
Yes.
Yeah, there was a question from the chat if this repository is online. And yeah, okay, here we go. Right, great.
No,
sorry.
Iridium, just to answer the question fast, is Iridium that he is. Thank you.